In the last section, we learned about all the experiments done by Faraday to understand the relationship between the magnetic influence of a magnet or an electromagnet and the EMF induced by a change in that magnetic influence or effect. Now, influence and effect are very vague terms, so we need to be more specific in what we are trying to say, more precise. So we will use the terms field and flux, just as we learned the concepts of electrical field and electrical flux. So what we are going to learn now is the concept of Faraday's law of induction. So what is Faraday's law of induction? Let's start with the statement. The statement is that the magnitude of the EMF induced in a circuit is equal to the time rate of change of the magnetic flux linked with that circuit. What does this mean? Well, first of all, let us see what is meant by induction. The word induction is related to the word induce. And to induce something means to create a response or to persuade some kind of effect. So in this case, when the magnetic flux linked with a conductor, with a circuit changes, and EMF is induced in that circuit or in that conductor. What is the meaning of magnetic flux? Let's say that we have a magnetic field, let's call it B, and it exists in a given region of space. And in this region of space, we have a surface. And this surface, the orientation of the surface in space can be specified using an area vector. So we will draw a vector perpendicular to the plane of this surface. And this is our area vector A. In that case, the total magnetic flux passing through this area or this area element can be denoted by the symbol phi b. This is the symbol for magnetic flux, and this will be equal to the dot product of the magnetic field and the area vector. Or in other words, this is equal to the magnitude of the magnetic field multiplied by the magnitude of the area multiplied by the cosine of the angle between their vectors. So this gives us an idea of the total effect of the magnetic field in that given area, in that given region of space. So let us revisit the statement of Faraday's law of induction. The law of induction, what does the statement say? It says that the magnitude of the EMF, which we also call voltage, induced in a circuit. So the response that a circuit gives us is equal to what? It is equal to the time rate of change in other words, the rate at which the flux is changing with respect to time of the magnetic flux linked with that circuit. Or the magnetic flux which is interacting with that circuit. We will understand the statement in more detail with the help of a diagram. If you recall the previous experiments, you will note that a lot of Faraday's work happened using magnetic field coils. What he would do is, he would use a metal coil, and this metal coil would have a current. Let's say a current I is flowing through this coil, and this current flowing through the coil is creating a magnetic field. So the magnetic field, as we have already learned, has no beginning or an end. It is circulating in a sense. So we have all of these closed loops. And this is the magnetic field coming out of a solenoid. Now, this magnetic field has some interesting properties. First of all, if we were to look at the field lines which are emerging from this end of the coil, these field lines will have a orientation and there will be a certain strength associated with them. The closer the field lines are to each other, the stronger the strength of the field. The farther apart they are, the weaker the field. Now, if we were to assign this region of space here, doesn't have to be any particular shape, this region of space through which the flux is linked, we have to figure out how much flux is flowing through this region. Now, we already learned that the flux linked with a given region is given by phi b is equal to the product of the area and the magnetic field. How do we use that concept here? Well, this region has no definite shape, but we can break it down into a lot of smaller regions. And each of these regions gets a name. This is known as an area element. An area element is vanishingly small and it is oriented in a particular direction. Because this is a curved surface, all the area elements are pointing in different directions. And if we were to draw a vector perpendicular to the direction of a given surface, that would be its area vector. And the length of this vector would depend on the size, the physical size of the area. Here, we observe that number of lines of force, magnetic lines of force, are moving through this region. Now, if we were to find the values of the flux, phi 1, phi 2, phi 3, and so on, that would be equal to A1 dot B plus A2 dot B plus A3 dot B, assuming a uniform magnetic field, and the total sum of all of these area elements together would give us the net value of which is passing through this given volume. What Faraday discovered was that the change in the flux magnitude with respect to time. So if the amount of flux passing through this volume is changing with time, will be exactly equal to the EMF generated inside this region. So if you have an electrical circuit in this region, an EMF will be induced in this region, and as a result, there will be a flow of current in this region. Mathematically, we can say that E, that is EMF, is equal to negative d phi b by dt, where phi b is the magnitude of the flux and d by dt is the derivative, the rate at which the linked flux is changing with respect to time. And the meaning of this negative sign is something that I'll explain to you in the next session. If we are dealing with a solenoid, that is a coil which has many turns, we can find out the EMF for a single turn, and if we were to multiply this with the number of turns, that will give us the total EMF induced in this coil. Now, as to why there is a negative sign here, we will see this in the next session.
Manorama Horizon. Learning made simple.